It's going live now.
Good evening and good afternoon and welcome to another Science for Today forum hosted by the Faculty of Science and Technology of the University of the West Indies. The Faculty of Science and Technology aims to be the go-to place for science, knowledge, research, and solutions. With this strategic vision in mind, the Science for Today forum series was launched in September 2018. Through this initiative, the Faculty of Science and Technology brings together academics and professionals from the private and public sector to contribute to the science discourse regarding topical issues that affect our society, while highlighting the of science in everyday and life. Today, the faculty has hosted 13 fora in the series. Featured issues have included COVID and the environment, risk is opportunity, ready for the big one, the immense value of forests, plastics, the science behind the ban, and minimizing mosquito mayhem. The series are free of cost and open to all members of the public. Today's forum is looking at landslides, and we have with us Professor Simon Mitchell, Mr. Knut Ricketts, Ms. Diane McPherson, and Dr. Wayne Reed. So as usual, we have representatives from academia, the public sector, and the private sector. Landslides have come to the fore once again, even though they're constant features of living in Jamaica based on our terrain and the geology of the island, and of course, the heavy rains that we get during our rainy season. Last year, in October 20, we had a very startling headline: heavy rain causes deadly landslides and floods in the Gleaner. And at that time, 2 persons unfortunately lost their lives during a landslide event. We can, of course, count the cost or put a value on infrastructure, but of course, there's no value when lives are lost. More to the fore, in November, there was the landslide on the Gordon Town Road that made hundreds of persons get disconnected, and also posed challenges for the farmers and other businesses that were further up in the hills behind it. There were also landslides on the Irish Town Main Road, and after that landslide, there was another major event where the road broke away, leading to Gordon Town, Mavis Bank, and of course, the districts beyond. There's a very high cost to these events, and of course, the effect on lives and livelihoods. So this evening in our forum, we're going to be looking at landslides, infrastructure, and housing construction. We have a very interesting group of panelists. We're going to start our proceedings this evening with Professor Simon Mitchell. Professor Mitchell is my colleague in the Department of Geography and Geology, and he's an English import. His early years were spent in the Cotswolds in southeast England, where he developed his love of geology. He received a first-class honours degree in geology from the University of Hull in 1989 and a PhD in geology from the University of Liverpool in 1993. He joined the Department of Geography and Geology at UWI in 1996. He's been promoted from senior lecturer in 2000 and is now the Professor of Sedimentary Geology, a post he's held since 2006. He's widely published, having more than 140 peer-reviewed papers and 195 papers at scientific meetings. Most of his work is centered around the Caribbean regions. His research interests lie in the Mesozoic and Cenozoic sedimentology and paleontology. the stratigraphy and geology of Jamaica, and the development of geological resources, as well as the geological evolution of the Caribbean region, are among his ongoing research activities. He's a recipient of the Moore Medal from the Yorkshire Geological Society in 1989, the Gleaner Honor Award for Science and Technology in 2011, and the Chubb Award for Excellence in Geology in 2013. And he rounds out his awards with the Vice Chancellor's Award for Excellence in 2014. We welcome Professor Mitchell to make his presentation on landslides in Gordonstown, Irishtown area, geology, causes, triggers, types, and consequences. Professor Mitchell.
Okay, thank you. All right, let me find it. There we go. Okay. The originally is supposed to occur on the 4th of March, but it's been changed to the 3rd. So that's one I missed. So I'm just going to give you a little outline of what I talk about. I'm going to really start with a little bit of the background geology of the area and why it is, how it actually is at the present time. So as a bit of simplified geology there, what we're going to talk about that. I'll then talk a little bit about the causes of why landslides happen, the triggers, which are really two, rainfall and earthquakes are the triggers. And of course, we're recently had rainfall being a trigger, but earthquakes can cause very, very significant landslides. For instance, Judgment Cliff is sometimes considered to have occurred after a very big earthquake. And then I'm going to go through 3 landslides that occurred in early November of 2020 and just show you the differences about them, why they happened in the way they happened. And all 3 were triggered by basically the high rainfall, and then a very quick discussion. I hope to not lose people with the geology aspects, and I'm sure one slide will lose people, but we'll work with that and we'll go through. Okay, so let us start. Okay, so basic geology of Jamaica. Well, we're interested in this eastern bit, adjacent to Kingston, heading up towards Irishtown. Now on this, I've shown some faults, and the faults are shown in red. And you can see that they come in from the east coast, where they're heading in from basically Haiti, and they come in and they turn up quite sharply. And this gives us what we call the Wagwater Belt, which is the main central feature that is between those 2 major faults. The lower fault also continues off across southern Jamaica. And really, this is a compression structure. So everything is trying to move from top right towards the left. So it's all trying to move in that direction, which makes this a very compressional zone. And the Gordonstown, Irishtown area, which I'm going to talk about, is sort of in that little rectangle there. But I'll just show you some of the other things. There are big blocks here. There's the Clarendon block, which is about 2/3 of Jamaica, and that's really the stable limestones. Okay, although it is deformed in places. And then you've got the Wagwater Belt, which is this deformed belt, which is quite a different story. And I'll talk a little bit about that just to put it in context. And then behind it, I have the Blue Mountains, which are actually pushed up over that. So everything is trying to climb up from the right to the left in this actual diagram. So let's go on and have a little look at what the geology looks like. So this is my current map for this area. So you can see the University of the West Indies down there by the Mona Reservoir. And then you go across a series of sort of northwest, southeast trending structures. Okay, and those structures basically define different belts within this deformed area. And I'll show you why they're significant. I'm going to just put some simple labeling on these. So number one is really, well, Kingston area, which is alluvium overlying limestones, and the limestones are exposed in a few places. So for instance, there you have, in the south, you have Long Mountain, and then you have another little bit of limestone in the top on the northwest area. So that's sort of the stable part. And everything further to the top right has been actually deformed over this. So first of all, we go to area 2, which is sort of the Jacks Hill area, which is a deformed belt of the same stuff of the Clarendon block, which is in area 1. But it's deformed and uplifted a reasonable amount, maybe a kilometre or kilometre and a half, and it includes Cretaceous rocks and some Eocene rocks. The Cretaceous rocks are problematic because they weather and they cause a lot of landslides in the Jacks Hill area. You come down to number 3, and number 3 is Dallas Mountain. And Dallas Mountain is a little bit of an oddment. It's actually not part of the Clarendon block. It's actually part of the Wagwater belt, that belt that's represented by 4 and 5 here. And it's strange in a way that it's actually upside down. And it actually represents what we call a nap, and it's been actually turned over and in place due to the uplift associated with these faults. When we go into 4, and 4 includes the area around Irishtown, or heading up towards Irishtown, and Gordonstown, that's made mainly of conglomerates, and those rocks are a lot older than the rocks over to the actual west. And the most interesting fact about it is that those have been uplifted very, very significantly. If you look at the ages of them and the known sedimentary thicknesses that we can measure that were deposited, those rocks have come up something in the order of about 10 to 12 kilometers relative to the rocks to the west. And then beyond that, you go into a series of igneous rocks, those pinkish colored ones there. Again, you can see really quite sharp boundaries. So those sharp boundaries are again faults. So what you get the feeling of is there's lots and lots of faults, okay? And most of the faults are lined northwest, southeast. And that is why this area is prone to landslide. You've uplifted these conglomerates, which are rocks which are not going to be very stable, but equally on top of it, if you're going to throw something up, you're going to carry it up 10 to 12 kilometers, you're going to deform it very, very significantly. And all those deformations yield to weaknesses in the rocks, which make them prone to actual landslides. I sort of went through that. I'm not going to go through that one again. Just to say that the igneous rocks are what we call the Newcastle Dacite, and they all give rise to fairly steep mountains. People know these areas, a lot of them. So that's just a nice view looking actually towards Catherine's Peak, and you can see the very ruggedness of the actual mountainsides there, and you can see why they are potentially prone to landslides. So let's just look at these rocks very, very briefly. I'm only going to talk about a few of them. The Wagwater Formation is the one which is the one we're concerned with today, because that's the one which has a lot of the landslides occurring in it, or at least the ones that occurred in November. And it largely consists of conglomerates. And here you can see a nice exposure of conglomerates made of big blocks of rock, which have been eroded off original volcanic deposits and then placed in this area. But associated with it as well, there are these things, which are, you can see layering in this, and these are bedded sandstones and shales. And these are some of the problems, because sandstones and shales, those layers, if they are orientated in the wrong direction, they can fail. And if they fail, what you get is you get landslides. And we'll see that that is one of the ones that's caused, or one of the reasons we have one of the landslides. And then I just thought I'd throw it in. This is the Newcastle Dacite, the igneous rocks. And this isn't bedding, and the previous one was bedding. These are joints. So these joints that have been created either by cooling, or more likely in this situation, because of the deformation they've gone through. And again, these are weaknesses in the rock, and joints are problems because if you get joints in the wrong directions, they can lead to landslides. So we have to understand all of these sort of things when we're actually looking at an area and trying to work out whether it's susceptible or not susceptible, why a particular part is susceptible to actual landslides. Okay, so some of the causes, risks, etc. Well, geology is obviously an underlying one. Okay, so the lithology, if you've got something that's prone to failure, it's obviously going to potentially give landslides. The tectonics gives you features in the uplift and deformation, sedimentary features, the bedding, I said, the layering, and those things can cause it. So all of these things affect it. But the risk factors are other things as well. The slope, the topography, how steep is it? Obviously, the steeper it is, the more likely you're going to get it. When we put roads in, we cut into the landscape. And in cutting into the landscape, what that does is undercuts and increases the risk of failure. We've got these steep slopes. If you clear the land of vegetation, you leave it bare, you increase the potential for the actual land to fall off. I mentioned the bedding, the layering. That can cause a problem if it's dipping in the wrong direction. And then, of course, joints, as I mentioned, and faults can cause problems as well. So the triggers, well, the two main triggers for the landslides are rainfall. And it's intense rainfall, often after you've had other rainfall, which really leads to this. So you get a certain amount of rainfall beforehand, which we call antecedent rainfall. And then you get a big amount of rainfall, a large amount in a short period within one day, and that will cause failures. In this case, we didn't see earthquakes, but earthquake can be another failure indicator, particularly if you've had this rainfall again and you get a big shake, you're going to get a lot of landslides. So what I'm going to do is look at 3 landslides, and these were associated with the rains associated with Hurricane Eta in November. Okay, so the little yellow asterisks there are the 3 landslides I'm going to talk about. I just label them L1, L2, and L3. L3 is the breakaway heading towards Gordonstown, and L2 is on the Irishtown Road, and L1 is actually just on the Gordonstown Road after the junction with the Irishtown Road. So those are the 3 I'm going to actually just briefly go through and explain what has gone on, how we can understand why the landslides happened. I'm not an engineer, so I can't come up with a solution for it necessarily, but I can tell you why they're actually happening. Triggers. So the rainfall is a very important trigger. And that was the main trigger that actually affected this area on the 7th and the 8th of November last year. And the first set of rainfall was in October, late October, and that was Tropical Storm Zeta that caused that. But the larger amount of rainfall was associated with Hurricane Eta, which was in those days in November. Earthquakes in this case weren't a problem. Okay, so this is some data from WRA, which Dr. Mandel is working with me on. And you can see in there the rainfall, and the rainfall amounts go up to 100 millimeters. So 10 centimeters, 3.5 inches. And you can see that you get this big spike at the end of October, which caused the landslides at that point. And then this very big spike with Eta in November, which is a trigger event for the 3 landslides, which I'm going to talk about. Okay, so landslide number 1, and various people have sent me pictures of some of these things as they happened, or very soon after they happened. And so this is number 1. This is the one just as you go onto the Gordonstown Road after you pass the turning to Irishtown. And you can see here the material has actually come down in this place. Here's another picture with them starting to clear some of the material away. And this is what it looked like when I actually got up there. And you can look at what the material is made of in this case. And here's the detail of what the material is made of. It's made of broken up pieces of rock. It's not solid rock. It's not bedrock. These are old landslides, and these landslides are remobilized to form new landslides. Okay, so this is a case of remobilization of material that's already been transported. Okay, the second landslide is on the Irish Town Road. And this is a picture of it. It's after it's been cleared. You can see the materials being cleared away. And you can see that in this case, a retaining wall was put in to try and actually stop landslides. Obviously, it didn't work. And you can see the large amount of area above that has actually failed. Okay, so there's another picture of where the materials come down. You can see failure surfaces at 2 different angles and gullies and things like this. Okay, and this is another picture of it, but this shows you more information about what is actually going on. If you look at the rocks, these are the sandstones and the shales, which I mentioned. And you can see there the orientation. You can just make out those layers which are dipping down towards the road. And that is where the problem is. Because what happens is that when you get heavy rainfall, the water gets in, gets along those bedding planes, and it makes it easier for the actual rocks to slide. So that when you get these very, very intense rains that come in and everything is already wet, what happens is you start getting failures, and there are also little joints in here, and it breaks away progressively up through these exposures. Okay, and you can see in this case, a lot of vegetation has also gone down through here. Now, it was about a year or 2 ago that they cut in to actually put the retaining wall in, and therefore they undercut this landslide or potential landslide, and that may well have actually helped, in fact, the fact that so much came down at that time. Okay, so we go on to the large one, which has really disrupted people, because landslides which come onto a road can be bulldozed away relatively quickly. But landslides which take away a road are much more problematic because you can't put a road back immediately. And this is the breakaway on the Cordentown Road. And the landslide deposits, I'll show you them in a minute, are below this, because obviously this material failed and went down into the river. Now, what I've indicated in here is some joints, okay? And these are weaknesses in the rocks. These are actually conglomerate rocks, but the failures in this case are related to these joints. And you can see that joint 2, and there's 2 places I'm showing joint 2 because it's a set of joints. It's not just one surface, it's more than one surface. These are almost vertical. And you can see there's one which is the failure, which is down below the road, and you can see there's another one which is above the road. So there will be more of them as you go into the cliff face. So what these are is these are weaknesses which can fail. And in fact, there are 3 joint sets in this area which are important. The second one is J1. Well, I guess the first one, but I'm going to show you some detail of J1 in the next image. Okay, so this is what the surface actually looks like. Okay, and joints or microforts might be a better description because they have moved a little bit. And you get these lines on the surfaces. And these lines are the striations that are left as one bit of rock, the bit that's now gone, has moved over the other piece of rock. Okay, so this is just looking at it again, and you can again see these. So J1 is the one that's running up parallel to that break there, and then it turns into J2 as it goes around the other way. So you get these faults or microfaults or joints systems, and it's these that have failed. So in this situation, what you've got is you've got the water has got into these joint systems, and because you then get the very heavy rainfall on top, the pressure builds up, and you get a failure that takes place. This is the view from below, and there you can see the landslide deposit, the material that's fallen down off this particular failure system. And if I come around here, you can see the 3 joints, okay? J1 and J2 are the ones we saw before, and not quite so easy to visualize from this direction. But J3 is another one here, which is climbing up towards the right. And so J2 if you remember back, was dipping towards us, and J3 is dipping into that face. And what they do is they actually form a wedge-shaped, and it's that that has failed, and it's that which has actually come out. Okay, so that is the problem in that situation. I'll also point out there was a retaining wall along here, and you can see there's no reinforcement in that retaining wall at all. So it really didn't help in preventing this particular landslide occurring. There's just another view of it showing the three joint sets. So there's one joint set there, one in the background, the vertical one, and one dipping down. And that gives you this wedge-shaped pattern. And it's the wedge-shaped pattern that's failed, and that has actually formed the actual failure which has taken the road away. We use these wonderful things called stereo nets, which I'm sure nobody will understand, except if there's a few geologists looking at it. But what this does is it plots up the surfaces, and you can see on there, I've got this thing that says wedge failure, and that is the wedge failure, and the slope is a curve in there. I'm not going to spend any time talking about that particularly, but these are the sort of diagrams we use to actually understand what the features are and actually how you can actually understand them. So just a quick little discussion at the end of that. So we have this antecedent rainfall. Up to 2 weeks before, 3 weeks before, we had repeated episodes of rainfall. So we had zeta and then we had eta, and we get rainfall which increases the pore pressures along bedding planes and joints. And so if we then get an event, and that could either be an earthquake, or in this case, it was a very heavy rain event, the heavy rain event can actually lead to the actual generation of the landslides. So Hurricane Eta was the trigger event in this case, with 30.8 millimeters of rain on the 7th and 94.8 millimeters of rain on the 8th of November. And the first landslide on the Gordonstown Road happened on the 7th, and the breakaway happened on the 8th. So the three landslides, well, landslide 1 represents a remobilization of pre-existing landslide deposits. So if you're going to try and protect against that one, you've got to put something in place that is going to protect places that you've already had landslides on. That's not so easy. Landslide 2 is a failure related to sandstones and shales, which are dipping down towards the road. So anywhere you have this situation where shales and sandstones are dipping down towards the road, have the potential for failures. And we see that repeatedly in many, many places around Jamaica. If you go to St. Mary, a lot of you near Highgate, you will know that you've got these places where you basically can't have the road that you wanted to build. It's had to go around it. It's the same thing. Sandstones and shales dipping in the wrong direction. So how the dip of the sandstones and shales is in these areas actually controls whether you get landslides or not. And the final one is landslide L3, the breakaway. And this represents a wedge failure within conglomerates, and that's associated with joint sets. And those joint sets are associated with the deformation that was originally related to the uplift of this whole area, which created this 10 to 12 kilometers of uplift. And that is why we start seeing these sort of things. And failures of joints are more problematic because you don't necessarily see them in the same way until they actually start failing. So there will be other places where the similar joint sets exist and which could fail in the future. So I think that is my complete little story of these recent landslides and how these landslides are actually being formed. I don't really need to say what the problems are associated with them. We all know what the problems associated with them are, but perhaps now we understand a little bit more about how some of these landslides happened and what their significance is and the problems that we have to think about when we have to basically try and come around solutions to actually stop them or mitigate them as best we possibly can. Okay, that's me done.
Thank you very much, Professor Mitchell, for your presentation. I must admit that I have a vested interest as I live in Irish Town and I have friends nearby, and I'm a part of a WhatsApp group for Gordon Town, and I encouraged them to listen in so they could understand a little bit of what led to the current situation that they're experiencing now. You use a very nice word, breakaway. They call it the brockway. So they understand their brockway a little better. So excited to introduce the panelists that I forgot to say who I am. I'm Thera Edwards. I am a member of staff in the Department of Geography and Geology, and I'm your host moderator for this evening. And I'm the moderator that's sort of with the panelists. And of course, I'd like to mention that for the persons joining us on YouTube, there is Dr. Andre Coy, my colleague on the Faculty Outreach Committee, who is helping to co-host with the YouTube attendees. So we're sharing responsibilities, and it is, as I said before, our pleasure to have you at this afternoon, now just turned evenings from. The next presenter is Mr. Knut Ricketts, a director of the Research and Mapping Unit of the Mines and Geology Division of the Ministry of Transport and Mining. Mr. Ricketts is a geologist, so he follows nicely on from Professor Mitchell, and his experience in the field of geology spans over 10 years, with him conducting geotechnical and geohazard investigations, geological mapping, slope stability analysis, natural hazard risk assessments, and the processing of development applications. So he's a nice segue to our next presenter after he finishes his presentation. He has been at the forefront of managing the execution of specialized engineering geological mapping projects for selected population growth areas across Jamaica, where the maps produced are used as decision-making tools for civil engineering construction, planning, and development. He's also worked extensively on a number of locally and internationally funded projects on natural hazard mitigation, storm surge mapping, quarry slope stability, assessments, and landslide susceptibility analysis. He serves as a member of the Technical Review Committee at the National Environment and Planning Agency, offering his experience in. He also serves in an advisory capacity on a number of project steering and advisory committees on multi-hazard vulnerability and risk management projects. We're proud to say that he holds a Bachelor of Science degree in Geology and Marine Biology from the University of West Indies, as well as a Master of Science in Coastal Engineering and Management. So he is a proud UWI, and we are also proud that he is a UWI alumna, and we welcome Mr. Ricketts to make his presentation on the Hillside Development Manual, a guide to safe and sustainable hillside development. Mr. Ricketts.
Thank you there. Thank you for that kind bit of introduction. Let me see if I can quickly share this presentation. All right. Great. All right, greetings everyone. Today I'll be presenting on the Hillside Development Manual as a guide to safe and sustainable hillside development. And for the sake of this presentation, of course, we'll be focusing on Jacksonville and surrounding environs. Now, just to give you a brief overview of the content of the presentation, we're going to introduce by looking at the rationale behind the Hillside Development Manual. Why is it that you need a Hillside Development Manual in the first place? Then we're going to move in looking at Jacksonville and the surrounding environs as a case study. We're going to look at some of the construction practices that we currently see within these areas and briefly run through the susceptibility of Jacksonville and the surrounding areas to landslides. After which, of course, we'll proceed to look at some of the guidelines of the hillside development policies and how these guidelines can impact on safe and sustainable hillside development. So the Hillside Development Manual is a policy document that promotes the safe and sustainable development of our hillsides. The manual was prepared by the Mines and Geology Division. It was back in 2014 to assist the development approval process. And this is in particular helpful to the processing of development applications, that's the building applications and your subdivision applications that are sent to the Mines and Geology Division. Now, the Hillside Development Manual aims to minimize the risks associated with hillside development, and this includes the risk of landslides, debris flows, debris floods, and erosion. Importantly, it functions to reduce disturbances in geologically sensitive environments. Now, the Jacks Hill and surrounding environment is one such geologically sensitive area that is prone to slope failure. Now, nonetheless, it is important to note that Jacks Hill is an area that is highly sought after for residential development, right? And what we've noticed in recent years is that there's a growing demand for residential development in the Jacks Hill area. Now, in addition, we've also observed a shift from your traditional single-family development to now your more dense multifamily development within this area. Now, I just want to use this opportunity to also run through real quickly some of the poor construction practices that we observe within the Jacks Hill area. We're not saying this is the entire Jacks Hill, but we're saying that this is what we observe within this area. And this is a part of the whole rationale as to why we thought we needed to put together a manual so that we can have better regulatory framework for hillside development. Now, what we noticed in the area that they were basically building on excessively steep slopes. And these weren't really single family developments. These were huge multi-family development, as you're looking at here in photograph A. In photograph B, this is an example of an unretained earth cut. And we find this very, very frequent in the hillside areas. Oftentimes developers, construction individuals, homeowners, they modify the site in such a way that it leaves extremely deep cuts, and these cuts are usually unretained. And when you leave these cuts exposed to the elements of erosion, of weathering, and you know, it can quickly lead to landslides, as Professor Simon Mitchell mentioned earlier. What we also notice is that there are a number of ad hoc development practices in the Jacks Hill area. As you can see in photograph C, there's a retaining wall that was basically damaged in order to provide access to a property. In photograph D, a bridge used for rooftop access to your house. You know, and those are some of the challenges with which we are faced in the hillside areas. Now, just to take a closer look at the Jacks Hill and the surrounding environs and the susceptibility of that area to landslides. Now, the geomorphological and geological characteristics of Jacks Hill are such that it predisposes the area to landslide occurrences, right? So it consists of a very steep topography, very dense drainage network. You find that erosion is very high along these slopes and the gullies. And importantly, the geology of the area is extremely problematic. Now, Professor Simon Mitchell did a good job of going through the geology, so I don't think I'll have to spend a lot of time in describing the geological formations and so forth. But what I will do is reiterate on how geologically diverse this environment is. There's a number of geological formations within a small area, and these geological formations are extensively faulted. Now, if you look along this geology map, you will see these east to west trending lines, northwest rather to southeast trending fault zones. Now, what these faults do is that they weaken the rock mass, right? So extensive faulting and fracturing of your rock mass, it weakens the overall rock mass quality and therefore increases the potential for slope failure. Now I want to draw your attention to these lobe-shaped structures. These lobe-shaped structures that you're looking at here in gray, these are colluvium deposits. Colluvium deposits in the landslide area, as you can see, are derived from granodiorites, the formation that's in green. Now, granodiorites, as Professor explained earlier, are intrusive igneous rocks. The mineralogy of granodiorites is such that it weathers down to produce swelling clays. Now, swelling clays undergo significant volumetric change when exposed to varying moisture conditions. So in a sense, when it dries out, it shrinks. However, when it's wetted, it expands. And so the derivatives of granodiorite are oftentimes problematic for engineering purposes. And these lobe-shaped structures are the failed derivatives of your granodiorite. These are colluvium. These are old historic landslide deposits. Now, this is a 3D model of Jack's Hill, and what it shows in the red lines, these are the landslide source areas. These are the areas from which most of the material would have been mobilized and deposited downslope. So these lobe-shaped structures that you're looking at within these areas, these are the colluvium deposits, and they are very much problematic for engineering purposes. Now, where you have just a thin layer of colluvium overlying your underlying massive or your dense bedrock, that is fine for development, because you can simply go in, you can excavate that material, you can replace it with suitable foundation material, and you'll be fine. However, where you have thick deposits of colluvium, it presents a challenge for engineering. And oftentimes you have to use very deep foundations. There are occasions where you find shallow foundations being used, but these are usually limited to raft foundations, as these foundations are usually very resistant to settlement, you know. Now, if you look at this photograph, you'll have an idea of what colluvium looks like. Now, colluvium is extremely loose material. Based on the review that I've done of numerous soil reports that were conducted in alluvium, what we notice are two distinct patterns. Colluvium that consists of coarse-grained soil, that's your sand and gravel particles, are generally very loose. They haven't gotten that time to get compact, you know, and to consolidate. While colluvium that is predominantly fine-grained, meaning your silts and your clays, they usually exhibit moderate to high plasticity. And that is somewhat problematic for engineering design. Now, photograph B also shows a road failure that occurred in colluvium in Jack's Hill, and this occurred in 1988. Now, just to take a look at some of the common slope failure mechanisms within the Jack's Hill area and surrounding environs. As Prof. Mitchell mentioned, there's a strong relationship between the geology and the landslides failure mode. Now, this is the failure at Garden Town, right? And what we find is that within the Wagwater Formation or similar geological formations that are blocky and extensively jointed, you typically find planar failures, right? You find planar, sometimes if it's highly weathered material, if it's highly weathered down to soil, you may get some rotational within that formation, but it's predominantly planar failures that you find within the Wagwater Formation. And that's because it is extensively jointed. Now, to the right, if you're looking at figure B, this is a wedge failure. Prof. Mitchell also spoke of wedge failures. They occur when you have two adjacent failure planes intersecting. And what happens is that that material generally fails along the line of intersection, and it creates a wedge, and it's so-called a wedge failure. Now, rotational failures are also common within the Jack's Hill area. Rotational failures, however, unlike planar failures, they're more complex, and they generally occur in deeply weathered soil. So for rotational failures, they usually have a curved slip surface as opposed to a planar slip surface that we just mentioned with a planar failure. You typically have some rotation, backward rotation along the head of the landslide. You find some amount of displacement along the scarp area of the landslide. Typically, you do have these transverse cracks at the foot of your landslide and a hammocky toe, which generally bulges towards the toe area of your landslide. Now, this rotational failure that we're looking at in figure A occurred in 1988, just along Jack's Hill Road, and it resulted in the destruction of this residential property. Now, debris flows are also common within this area. And a debris flow, of course, is just a hyperconcentrated flow of debris and and stormwater, right? Now, where the stormwater exceeds the concentration of debris is called a flood, and vice versa is called a flow. Now, photograph A shows a debris flood at Wilmington Drive in Jacksonville, and this occurred during the passage of hurricane, well, not hurricane, but tropical storm Gustav in 2008, while photograph B shows a debris flow in Hope Pastures following the passage of Hurricane Ivan in 2004. And now, having spoken in depth of the challenges towards hillside development and the susceptibility of the Jacksonville area to landslides, we're going to take a look at the Hillside Development Manual, the guidelines contained within, and how these guidelines promote the safe and sustainable development along our hillside areas. So, first and foremost, the Hillside Development Manual establishes a maximum slope gradient requirement for residential development in hillside areas. In accordance with the Hillside Development Manual, we do not permit development on slopes exceeding 30 degrees. And in fact, there are some slopes that we even have a lower slope gradient, maximum allowable slope gradient range. Slopes such as colluvium, right? With a thick deposit of colluvium, the maximum is 18 degrees. And of course, no development is permitted on slopes that are active. An active slope is one that is still unstable and showing signs of movements. So you may observe bulging along sections of the slope. You may observe tension cracks and so forth. And what that indicates that the slope is still active and may fail at any point. Now, the Hillside Development Manual provides guidelines for site modification. As we noted earlier, no development is permitted on slopes in excess of 30 degrees, and likewise, no cut and fills are allowed. Nonetheless, if this should occur, it would occur under special circumstances, unless the applicant can demonstrate to the division that the cuts and fills proposed within this area will better stabilize the slope. We do not permit cutting slopes that are greater than 30 degrees. Now, we do have a limit for cut and fills, and this is 4 meters. Cut and fills should also always be retained using the appropriate mechanical stabilization measures, such as retaining walls and so forth. Now, when your cuts are below an existing roadway, this can be very problematic. It can lead to destabilization of the roadway, and as such, we recommend that you have an additional setback from the roadway. As a rule of thumb, we usually recommend 2.5 times. That's the ratio of the cut to the distance from the roadway. So it's 2.5 to 1. Right? Now, the development manual also recommends that you avoid mass grading of your site. So when it pertains to those larger developments in excess of 2.5 acres and upwards, the development manual recommends that you grade the site in phases and avoid mass grading the entire site, as that creates problems of erosion. All right? Now, grading plans, of course, are generally required for all your building applications, as that will make us, put us in a better position to better review your application. Now, the hillside development speaks to slope stabilization measures, the concept of retaining wall, Gabion baskets. In areas where you might be prone to rock falls, we recommend that you screen the areas for these boulders, remove them, put in place rock burns, masonry walls, special barriers to mitigate the impact of rock falls. We also encourage terracing of your site, right, and stepping of your retaining wall. What you're seeing in photograph A is an excessively high retaining wall. This retaining wall is almost 15 meters high. Now, it is not only imposing and unattractive, but this also creates a safety hazard. If this retaining wall should actually topple onto an adjacent property, this could lead to serious damages and possibly death. Photograph B actually shows a failed retaining wall, which killed 3 workmen at Norbrook Heights in St. Andrew. So there's some amount of safety factor to reducing the height of your retaining walls. Now, let's move on to the erosion and control measures that are outlined in the Hillside Development Manual. So generally speaking, we usually recommend that you establish vegetation cover on bare slopes. So if you can look at this picture, this is what we want to have. Establishing vegetation cover on these slopes so as to reduce the potential for erosion. We recommend that you use your gabion baskets, Reno mattress, or commonly called your erosion control mats to prevent erosion along gullies. We also strongly recommend that sediments produced or generated on a particular site be contained on that site, pretty much like containing your stormwater runoff. Likewise, you should contain the sediments. So if you're developing a property and that property generates a certain amount of sediments, you are supposed to control that sediment. Use sediment traps, silt fences, whatever sediment control mechanisms that you ought to put in place, get them in place, ensure that you control your sediment. Your sediment should not be allowed to impact nearby properties. And this is one of the reasons why oftentimes when you have a period of prolonged rainfall, you generally find sediments on Tavistock Terrace, sediments blocking roads along Millsboro and so forth. So it's very important for us as developers to control the sediment that is generated on your site. Now, another stipulation of the Hillside Development Manual pertains to lot size requirements. Now, what we've observed in past years is that the minimum lot size for flat areas was being transferred to steep hillside areas.
To see if he rejoined.
Just heard, say, hello? I just heard, Tara? All right, so I'll continue. So what we observed in recent years is that the minimum lot size that we encounter on flat areas was being transferred to hillside areas, and that created a number of challenges, right? So what we recommend, however, is that with an increase in your slope grading category, you increase the lot size because you're going to need a lot more space to provide access for your property. You're going to need more space for cotton fields. You're going to need more space to put your sewage and so forth. So we encourage an increase in lot size with an increase in slope gradient. One of the stipulations of the manual is it also deals with problematic sites. Now, problematic sites or problematic rocks and soils are soils that are highly susceptible to geotechnical failures. Colluvium, for example, is one such material. And so we recommend that colluvium slopes exceeding 18 degrees are not considered for development. We also strongly recommend that geotechnical and geological reports be prepared for these sites. And generally speaking, we usually recommend deep foundations where necessary. Now, in closing, I'd just like to reiterate that the guidelines of the Hillside Development Manual are geared towards safe and sustainable hillside development. However, we need greater compliance to really make this a reality. We need greater compliance from the developers, from the engineers, from the architects, the builders, and generally all stakeholders. Now, I also want to use this platform to implore that all individuals who are involved in development and construction along the hillside areas visit the Mines and Geology Division for pre-consultation. Visit our website, download a copy of the Hillside Development Manual. A colleague once said to me that in the age of information, ignorance is a choice. And so I like to just encourage you all to conduct your due diligence. Thank you.
Thank you very much, Mr. Ricketts, for your presentation.
Okay, thank you, Tara.
I learned a few things. I continue to learn more about geography. This was a time that I hear presentations. So now I know a little bit about debris flows and debris floods. And of course, your map was a nice follow-on from Professor Mitchell's presentation. It was also interesting to hear about the manual and the recommendations it has. And in fact, because a lot of persons think that such things don't exist, that there is such a manual and the guidance is in fact there. We're going to move along. We'll do all the questions, even though there's some happening in the YouTube channel. We will continue with the presentations and then move on now to Miss Diane McPherson. Miss McPherson is a senior urban planner at the National Environment and Planning Agency. She's a veteran planning professional, having a lot of experience in urban planning and environmental management. And she has an active research record, having authored and co-authored papers on reports, not only on agriculture and food security, but settlement planning, especially the implementation of environmental laws. He currently serves on a number of such as the Forward Planning Committee and the Legal and Enforcement Committee. She also serves as a co-chair of the Environmental Impact Assessment Committee, and she provides technical support to numerous government and non-government organization committees. Again, I'm very pleased to say that she's an alumna of the University of the West Indies, Mona, where she earned her master's degree in urban and rural environmental management, and where also she gained her bachelor's in geography. So she's tied to the University of the West Indies and of course connected in again to the Department of Geography and Geology. She also boasts that she's a proud mother of one child and a budding entrepreneur. Please join me in welcoming Ms. McPherson to make her presentation on landslides and development potential. Ms. McPherson.
Okay, good evening, everyone. Why am I seeing myself upside down? Hold on. All right, so good evening, everyone, and it's my pleasure to be here to share with you the impact of landslides, especially as it relates to development potential. The first two speakers, they shared with us the science behind landslide hazards. What I'm going to try to do this afternoon is to basically share with you how we use the science to inform land use policy as well as to aid in the development approval process. So the outline of the presentation, I'm going to give you a brief background of the agency, look at the role of NEPA as it relates to disaster management, look on development potential as it relates to density allocation, landside susceptibility and land use zoning, the relationship. Also the relationship between landslide susceptibility and density allocation. I want to do some simple calculation as it relates to development potential, and then I'll conclude. So some background information. NEPA was established in 2001 as an executive agency. It's an amalgamation of the Town Planning Department, Natural Resource Conservation Authority, and the Land Development Utilization Commission. NEPA largely functions as an advisory, regulatory, and enforcement agency, as well as planning, and we deal with planning and environmental issues. Our mission is to promote sustainable development by ensuring the protection of the environment as well as orderly development in Jamaica. Now, what is the role of NEPA in the disaster management process, especially as it relates to landslide hazard? Now, there are three critical processes that is involved in development planning, and that is development planning, development control, enforcement, and monitoring. When I speak about development planning, I'm basically talking about the preparation of plans at the national level as well as the parish level. It also involves the preparation of the development order under the Town and Country Planning Act. When I speak of development control, which is the implementing arm of planning, talk about the processing of application. And at NEPA, we process application for environmental permits. And based on the category of the development, an EIA or an impact assessment may be required. We also make recommendations to the municipal corporations or local planning authorities, as some may know them as, on all subdivision application in Jamaica, and also all development application that is sent to us by the municipal corporation. There is also the appeal process, and this process normally kicks in when a planning approval is denied. The developer or the applicant can make an appeal to the minister, and based on additional information that is presented to the minister, he may grant permission or he may uphold the decision of the agency. Now, when we talk about development potential and density allocation, what are we talking about? In this case, I'm going to be looking at development potential as the best and the possible highest use of the land. And for this presentation, I'm going to be focusing on residential development potential. And that is basically the maximum number of units that can be constructed on a specified lot. And this is highly determined based on the density allocation within a particular area. Now you may ask, how is density allocated? Now I'm just going to share with you briefly how this is done. You have a settlement hierarchy where you look on the level of the settlement, whether it's a major settlement, a medium or a small settlement. We also look on the settlement importance. The highest densities are normally concentrated in like the urban areas and along selected corridors. And we normally have the lower densities in areas that are outside of the main urban centers. And we even have much lower densities in environmentally sensitive areas. Okay, so when we look on landside susceptibility and zoning, I'm just going to show you how it is that we transfer or how the science relates to the land use zoning. So the landside susceptibility map that was prepared, that information was used in terms of how we allocated land use zoning. So the areas that had the least susceptibility, those were the areas that had the highest developmental use. So those areas where we have most of our residential development, our commercial development, our office development. In the areas that is more susceptible to landslide, we normally focus lower scale type of development in these areas. In terms of landside susceptibility and density allocation, we also see a similar pattern and trend. The areas that are least susceptible to landslide normally has a higher density, whereas areas that are more susceptible to landslide, we normally encourage lower densities in these areas. In addition to lower densities, we are also guided by the hillside development policy. So in those areas, these areas, separate and apart from the density that is allocated in these areas are also subject to the hillside development policy, which may also impact the actual density that is given for development in these areas. So in addition to the general land use and the density guideline, applications, as I said before, are greatly subjected to the hillside and development policy that is prepared by the Mines and Geology. The things that are the additional information and the additional criteria that we look on is that the areas, the non-developed areas, we don't normally include them in the development calculation. Slope in excess of 30 degrees or unstable slope, we don't recommend them for residential use. However, there are certain circumstances, extraordinary circumstances, where non-residential development may be allowed in some of these areas. And there's also where the developer can prove that the mitigative measures that they plan to employ is sound. They may also be allotted the required density for that area. All right, I'm just going to do a simple calculation to show you the impact that landslide has on the potential development of a land. And I'm going to be using an example from the Kingston and St. Andrew and Pedro Keys Provisional Development Order 2017. Now, in the Barbican local planning area, the density ranges from 250 habitable rooms, from 75 habitable rooms to 250 habitable rooms per hectare. The main built-up area within the Barbican area is normally like 125 to 250 habitable rooms per acre. And as you move further out into the suburban region, it's normally 75 habitable rooms per hectare. However, as I said before, the areas that are subject to the hillside development policy, they may actually get a lower density than the 75 habitable rooms per hectare. So I'm going to give you a quick example. Say, for example, we have a piece of land which is 5 hectares or 1.2 acres. At a density of 75 habitable rooms, that applicant will be allowed, is normally allowed 38 habitable rooms for that size of land. However, if that piece of land is highly susceptible to landslide based on additional investigation, and say, for example, the density is lower to 50 habitable rooms per hectare, what the developer would actually get is 25 habitable rooms per hectare, which basically equivalates to a minus 52% loss in terms of the amount of habitable rooms that he could have gotten on that piece of land. So right then and there is where a conflict develops in terms of the developer and the regulator, because outside of the policy, they are saying that they can get X, but with the policy, they are saying that they are getting less. And they are in the business mainly to maximize on their return. So how is it that we go about striking a balance? So what we do, separate and apart from the general policy that we use, we also conduct a site, and we also recommend a geotechnical assessment of the site. And basically the reason why we request this information, we want site-specific data, and basically to determine what is the actual vulnerability of the site. We also require the geotechnical engineer to assess the nature of the landslide hazard, and also the type of hazard, whether it is shallow, deep, etc. And what are the best mitigative measures that can be used to reduce the risk of that site. If it's a case that we are satisfied with the geotechnical assessment and the mitigative measures that are actually recommended, the applicant may get the 75. However, if it's a case that whatever it is that they are recommending is not feasible, we will maintain that that site would actually get a lower density. So in concluding, the potential impact of landslide impacts land use zoning allocation. The higher use of land, we normally concentrate them in the areas that are least susceptible to landslide. The less intensive uses are recommended in highly susceptible areas and also low residential densities are also recommended in areas that are highly susceptible to landslide. What we see happening is that because landslide, the impacts of landslide can be very devastating, it actually can lower the development potential of a potential site. which in and of itself creates conflict with users of the land. So for us as planners, for us as regulators, is how we go about finding creative solutions to strike a balance between human and environmental protection and economic growth. So that is why consultation is very important. Education is very important. And that's the end of my brief presentation. Thank you.
Thank you very much, Ms. McPherson, for your presentation. And I am learning with each presentation this evening. So I learned a little bit about how densities have been applied in landslide prone areas and the whole process of density allocation. So we continue to journey together to learn a lot more about landslides, not only the geology that leads to them occurring, but some of the considerations for development through things such as the Hillside Manual, also the development and planning concerns and technical considerations that are applied. And now, having looked at the geology and the regulatory side of things, we turn to our final presenter for the evening, Dr. Wayne Reed. Dr. Wayne Reed is our private sector representative this evening. He's a registered professional engineer in Jamaica, a fellow of the Jamaica Institution of Engineers, a fellow of the American Society of Civil Engineers, and an associate of the Chartered Institute of Arbitrators. He has over 45 years of experience, mainly in consulting engineering in Jamaica, and his specialty is structural engineering and civil engineering. He's also worked extensively in project management as well as an arbitrator and adjudicator. He was awarded a PhD and an MSc in structural engineering from the University of Waterloo in Canada, a diploma in project evaluation and investment programming, and a BSc honors in civil engineering from the University of the West Indies. Here we go again, another UWI alumna. Dr. Reed is a director of the Gentech group of companies and has worked extensively in both private and public sectors. He's a past president of the Jamaica Institution of Engineers between 1980 to 81. He has been a chairman of the Jamaican Cricket 2000 Limited and the local organizing committee for Cricket World Cup 2007 during the period 2004 to 2008. He served as chairman of the National Water Commission from 1989 to 1995, and he was also managing director of NROC from 2001 to 2006, as well as its chairman from 2012 to 2016. He's been awarded the Order of Distinction, Commander Class in 2006. Active member of the Trinity Moravian Church, enjoys reading, scuba diving, and as you can see by his involvement in cricket, an avid sports fan. He's married to Dr. Janice Reed and has 2 children and 2 grandchildren to round out the things that he's proud of saying about himself. At this point, we welcome Dr. Reed to make his presentation on engineering design and landslides. Dr. Reed?
Thank you very much, ma'am. I'd like to thank the university for inviting an engineer to join them on this forum. The presentations before have described very clearly the phenomenon of landslides. And all of the factors are to be seen widely in Jamaica. First thing I talk about was on slopes. And we know that in Jamaica, we are more mountainous than flat. What makes it even worse in a way is that the mountain range runs east to west on a very narrow width of country, leaving not much plain either side. And to go back to sort of historical events, after the emancipation of slavery, 1834, many of our forebears decided to leave the flat areas where they were enslaved and go up into the hills. So we got the first set of roads, tracks that they were going up into the hills. The development of these tracks over time created roads, main roads that they became. But at the same time, as your previous presenter, the planner, would say, there was land development on either side of these roads. So it wasn't just a matter of an access from the southern side of the country to the northern side, or in going up into the hills, but it's a matter of access to land, both for housing and for agricultural purposes. Come the 20th century, there was the need for development, further development of these roads and other infrastructure. But you had the land development there already. So you really didn't want to move people out their land. And therefore comes the development of these tracks into roads. There have been very few instances in Jamaica where one has been able to do a proper scoping of the land that is going to be used for road development and determining the problems that can occur, including landslides. One of them was Highway 2000 East-West, where before designs were even started, an environmental assessment was done on a corridor which was 1 mile wide, so that anywhere within that corridor, the road could be placed depending on what the results of that assessment was. Coming back to what I said, mentioned before, there was no possibility of having any assessment in widening roads and in putting in infrastructure in Jamaica. Land development had already taken place. So what was required was better access. And this cry continues all the way. So that we get this phenomenon of landslides in our hilly areas. And as was mentioned before, highly dependent on the type of soil, also highly dependent on the placement of the location of our geological fault lines. And it can even occur in rocks, boulders, or whatever it is. In any event, the natural stability of the slope is disturbed, and masses of earth and trees and everything come flowing down. As was said before, it is mainly caused by heavy rainfall and sometimes by earthquakes. But most of the landslides, I put it in Jamaica, are really caused by human intervention. And that's where the engineer comes in to try to reduce the possibility of landslides due to this human intervention. The first thing that the engineer has to do is to examine the options presented to him. And he has usually 3 constraints working with. He has a location constraint. He can't move the road. Second thing is the cost. The road has to be widened, but within a budget. And the third thing is the time. For example, we have heard about the problems out on the Garden Town and Irish Town breakaways. People have to be living and people have to be commuting, and therefore you can't spend a lot of time in trying to figure out what is to be done. Something has to be done very fast. So that you have the options that you have to determine, and within a very fast and based on engineering principles, determine what the options are and what the costs are for each option. At times, you can come up with alternate routes, as was done again up at Garden Town, not necessarily a very good alternate route, but an alternate route nonetheless to help to ease the pressure and coming up with a good solution for the Gordon Town breakaway. The problem with that is that in some instances, it does not ease the problem, and in some instances you can't get the land to provide these routes. Now, in the first instance, in terms of infrastructure, the main problems that you have with the landslides is in the building of new roads or in the creation of widened roads. In some instances, it has been left to nature to help with the wide. One of those roads, for example, is the first part of the Junction Road from Stony Hill area to Granby Hole, where there have been numerous landslides, sometimes rock slides, and they were cleared, and in the clearing, there's a little bit of additional width to the road. If you will all remember or note that the hillside there, particularly on the left side going northwards, before you cross at Grandy Hole, is extremely steep. The second thing in terms of the road widening is a matter of the drainage that has to go with it. Unfortunately, in Jamaica, we don't take drainage very seriously in our construction. We noted, for example, a recent heavy budgeted expenditure here in the corporate area, that we did a lot of road construction and very little drainage and ran into problems most at the end of the road construction. So it becomes even more difficult when you're dealing in heavy terrain, in hilly terrain, in that you have these natural streams running out of the hillside, sometimes down the hillside, and this is not taken into consideration in the construction of the roadway or in the widening of the roadway. So there's a need for proper assessment of the drainage requirements that are required. There are other structure elements which are now coming more into vogue in terms of the hillside problems, and that relates to water supplies and to a certain extent to sewage treatment, collection and treatment, more so for water supplies, because the pipelines, as one of the former presenters stated, people are moving more up into the hills, in the Jacks Hill, Upper Norbrook area, and they need water. And the water is not up there. So it is coming from the lower areas. And these pipelines also can create problems and lead to landslides in the areas. The problem, again, in terms of the mitigation, how are we going to solve the problems of preventing the landslides, is a matter of, there are a number of things, a number of ways, I should say. One is the construction of retaining walls. Now, unfortunately, in a number of cases, the construction of the walls has led to the possibility of more landslides. And it happens just with planar landslides, as the land just slipping down a slope, but rotational landslides, as was mentioned by one of the presenters, where you get a slip circle, so to speak, formed. In that, the foundation for the retaining wall does not go below the possible slip area, the slip circle. And therefore, what it does, it gives an additional load on the slope, which doesn't help at all when rain comes. So that human intervention with poor engineering and poor construction is one of the problems that we have. The other problem is the strength of the wall. Let's say the wall is properly located. In most instances, the material used is rock, and for good reason. In terms of the location of these walls, it is not very easy to go and put a reinforced concrete wall. In fact, in one of the presentations, it was noted that the wall had no reinforcement, but I don't think the wall had no reinforcement. It didn't have enough gravity rock reinforcement because the gravity wall in itself is a method of reinforcing for the prevention of overturning. The positioning then of these walls can create problems. As was noted in one of the pictures shown by one of the presenters, where the wall itself did not prevent the slipping of the slope, and in fact, encouraged the slipping of the slope. So that in terms of infrastructure, and particularly with, it is a matter of first locating the road. If you have the chance, as I said, it rarely occurs where you have a chance to locate a new road properly and therefore take into consideration all of the factors. Or where you are widening roads, as happens frequently all the while in Jamaica, it is necessary to take into consideration the type of slippage that can occur, and therefore how we are going to position retaining walls to prevent that slippage. It is also extremely necessary to take into consideration the drainage, because it is unfortunate that quite a few of new widened roads don't have adequate drainage, and therefore they lead to destruction in a very short time. The intervention that I spoke about, the human intervention, which caused landslides, is even worse with the matter of housing. The presentations made by the representative from NEPA and also from the Mines and Geology spoke of developments which came under their order or scrutiny. The problems that we have are not necessarily confined to those. They spread to people who have to find a cottage somewhere. There may be a family land, or it might be a piece of land that is leased. And there's a lot of leasing that goes on lands, not necessarily even owned by the lessor. And in this case, somebody gets a little piece of land and puts up a dwelling. And these dwellings are not necessarily light dwellings. They are formidable dwellings. Comes the heavy rain, the load which has been imposed on that slope by these dwellings just creates a problem with the slope, and we have the landslide. So what is required in those instances is enforcement of our rules and regulations, because in most instances, the people who put up these dwellings are not going to engineers to get any advice. They are getting someone who's a local contractor to come and help them to do it. And they know they don't necessarily put up one total house at one shot. It's an addition, a little bit addition, and as the family grows, and they go closer and closer to the edge. So that the problems that we get with housing, whereas it is controlled in a certain respect by those who have to get development permits, the problems are probably worse in terms of the number of people affected by those who do not get permits, but are still allowed, so to speak, to continue to put up their dwellings. And in this case, the type of dwelling really doesn't matter very much. It's more the location, because even if the house is relatively light, let's say it was made out of wood rather than out of concrete, the fact that it is perched probably at the edge of an unstable cliff or on a slope which has been eroded before and has probably been undercut and is just waiting to come down, that these are the problems that exist, and they are unengineered solutions to the housing problem. So that if we can put more effort into enforcement of occupancy of land to prevent people from getting into these problems, then we would possibly have less problems after heavy rainfall. So that in closing, let me say that in terms of infrastructure, there is a greater possibility of an engineering input, particularly with roads. Unfortunately, in the matter of widening of roads, there are certain factors which prevent a proper design, and sometimes without any proper analysis of what is to be done. And in the housing areas, there has been a very good approach by successive governments in getting control measures in place for those who come in to get permits. Unfortunately, there are a large number of people who are not probably interested in getting a permit. They just want a cover over their head. And those are the people who get into a lot of problems with landslides after heavy rainfall. Thank you very much.
Thank you very much, Dr. Reed. And of course, as I indicated when we had our first conversation about your participation this evening, you did bring a nice closure to the presentations we've had, where we started with the geology, we looked at the development planning, approval, the regulatory, and of course we saw the response in terms of the engineer who has to grapple with all of these factors, what the geology is, and of course what the development guidelines and permissions process say is allowable when arriving at the engineering solution. Thank you very much. So we've had a very, very fulfilling afternoon, now evening, with some very rich presentations. And of course, while we have been listening, there have been a number of questions within the YouTube participants. So I'm going to go through some of those questions now. And of course, the relevant presenter who can respond to the question is free to unmute and provide an answer. So from Anna Pereira, she's asking if the Hillside Development Manual, is it publicly available? Mr. Ricketts?
Yes, it is. The Hillside Development Manual can be downloaded from the Mines and Geology Division's website.
Wonderful.
Yes.
And she also continued by asking what special physical or natural measures can be used to reinforce slopes. She referred to solutions that might involve vegetation or retaining infrastructure. I guess she's looking beyond the standard retaining wall. Yes. I had mentioned vetiver grass, which I know is used in some parts of the world, and we've also used it here, and Macaferi matting. But you can also suggest some other alternatives besides the standard cut stone retaining wall.
So her question, let's deal with the physical structures first. So outside of the traditional mechanical slope stabilization structures, such as retaining walls and your typical gabion baskets, you can actually use, and this is, you can actually use tire soil retaining walls. Now, there was a project, Mosaic project, that was conducted by ADPEM back in 2014-15, I believe, where we looked at using tire soils for slope stabilization. We see a number of communities across Jamaica, and we actually constructed a number of tire soil retaining walls, which are now still standing. But however, it must be constructed by professionals. So that's one non-traditional measure for slope stability, right? As it pertains now to natural measures, she mentioned plants. Caliandra plant, I'm not sure if you're familiar with it, but this specific plant species is extremely resilient. It has been used on a number of projects for stabilizing quarry slopes. Now, keep in mind, quarry slopes do not consist of soil. It's dry, very, very dry limestone slopes. These areas, there's, very little soil for plants to really grow upon, right? However, this plant is so resilient that it establishes itself even on these areas, and it grows very well. It stabilizes slopes by virtue of having deep root systems, and it has proven to be very effective.
Okay, wonderful. Dr. David Smith was asking, does setting a slope criterion, for example, greater than 30 degrees, take into account the geological factors described by Professor Mitchell, or should the guidelines take into account other factors?
All right. So if we go back to the initial origins of the hillside development manual, right? Our initial slope gradient was at 25 degrees. That is the initial limit that we had, right? And out of consultations with the architects, engineers, the planners, a wide range of technical individuals, it is at that stage that we agreed on 30 degrees. So that 30-degree limit took into consideration the geological factors, the planning. It took into account a wide range of factors. And so, yes, it's not just geology, but a number of factors.
The next question, I think, also directed for you. Well, I think it's more also for Ms. McPherson, as persons associated with the approval and permit planning process. For density requirements, will we also look at water availability, traffic management, waste disposal, sewage disposal, sewage concerns, and the general visual appeal of the city, not just slope and geology to decide habitable rooms?
Good question. For the purpose of this presentation, I only mentioned the impact of landslide. However, when we're doing the density allocation, all of those factors that were just listed are actually considered in how we allocate density across any geographic area of the island.
Okay, thank you for that response. And continuing on the subject of habitable rooms, Anna Pereira is asking, is the specification for a habitable room based on square footage? I think that's what she wants to ask.
I'm trying to understand the question.
Basically, what she wants to know is how do you arrive at the habitable room number? I think that's what she's trying to get at. If she could type it in the chat again, we could get some clarification. Anna?
Okay, normally when we're doing density allocation, we normally have a range in terms of high density versus low density. How we actually derive at the actual number of habitable rooms, we look on what is the allocated density for that parcel of land. We look on the size of that land, and then we do the calculation to determine how many habitable rooms you can actually get on that particular size of land.
Okay, thank you, Ms. McPherson.
That's helping. Is that helping?
I think it is. I'm monitoring the chat to see if she types in anything else. We have a question from Linda Johnson Bowler. Are there different regulations governing development of land in areas where earthquakes trigger landslides and those where rainfall trigger the landslides?
That is okay. We have the general development policies, and as I said before, we are also guided by the hillside development policy. But in addition to using the general policies, as I mentioned earlier in the presentation, we also do site assessment to actually determine what is the actual vulnerability of that particular site. So as it relates to landslides triggered by rainfall as opposed to landslide triggered by earthquakes, those would have been picked up in the assessment of that particular site, and then the applicable density would be applied to that site.
So I hope for Linda Johnson Bowler that the question was answered. If you need any clarification, you can indicate it in the chat and we will get the further clarification. I just wanted to, yes, she says thank you. So she's actually had her question answered, Ms. McPherson. So thank you for that response. I don't know if there are any other questions coming from our audience on YouTube. Please go ahead and type your questions in the chat and we will direct them to the presenters. So I'm just going to be just looking back at the discussion journey of this afternoon and evening. Through Professor Mitchell, we looked at 3 current topical landslides in the Gordontown, Irishtown area. And the fact that while these landslides are within a similar geological area, that they had very different causes. One occurred through remobilization, another occurred through failure of the sandstones and shales that were dipping. And the final was actually a wedge failure with the conglomerates from a 3-joint set. I was paying attention and taking notes. I see where my colleague, Dr. Robert Kinlock, was saying that he hopes the urban planning students are listening. So like a good student, I have been taking notes today. And from Mr. Ricketts, apart from generally introducing us to the Hillside Development Manual, we were also able to see a little bit more about debris flows and floods, and of course some alternate engineering solutions using natural options such as Caliandra, vetiver, and of course tire soils, which have been shown to be quite resilient in terms of their durability as a solution. From Dan McPherson, or planner from the National Environment and Planning Agency, we looked at some of the concerns for landslide-prone areas in terms of adjustment to densities, and of course the whole process of evaluation for and planning approvals. Dr. Wayne Reed brought some very good balance to this evening when he talked about the constraints. We're an island state. Jamaica has a lot of hilly, mountainous interior. We have in the eastern end of the island in particular susceptible geology. And of course, because of the small island developing state, we don't have a lot of options for, we'll just go somewhere else or do this somewhere that's more optimal. Sometimes we have to work within the constraints of the area. So we start off by trying to locate infrastructure such as roads properly. But sometimes when we have to widen a road, we may then have to take into account that we will have some amount of slippage and what kinds of retaining walls and retaining work will need to be done. We have, of course, cost considerations such as time, the persons in Gordon Town I know are eagerly marking the months on the calendar. They have been so-called incarcerated since early November, and it was only just some weeks ago when the alternate route through Savage Pen, which has been acknowledged not to be an optimal bypass or alternate route, but still provides a means of them having a road which is a shorter distance for them to use. That bypass road through Savage Pen came in at a cost of approximately $65 million. And the actual repairs to the Brockway, is currently budgeted at $195 million. So there's a lot of money at stake, and of course, the time to effect works, because the breakaway repair is supposed to take 6 months, all things going well. And so in the meantime, there is this culture brought to the commuting public, and there's the impact on livelihoods because we have coffee farmers and other interests beyond that breakaway. So, and the 5 points from Dr. Reed's presentation that is very key, and we see it all the time. I've seen it in the Gordon Town WhatsApp group chat: drainage, drainage, drainage. You're building a road, but where's the drainage? We don't want to lose this road. And it was in fact the way the water was channeled that we understand led to the failure of the road at the breakaway. In addition to the geology, it was a drainage issue at the time during the heavy rains. So we've had a journey this evening looking at a number of things from different perspectives. So I don't know if there's anything that any of the presenters would like to add at this point. Any closing thoughts, anything that they might have wanted to say during their presentations, they're free to do so at this time.
Sarah, I will just say one thing, if I may.
Sure.
I think one of the things that is required is a holistic approach to these sorts of things. I think you have to go from the basis of understanding the problems from the geological side, going all the way through how we plan these things, and ending up with suitable engineering solutions. I think it's got to be applied all the way through. And then we can look and point at various places where we know recently that has not happened. Northern end of Junction Road, for instance, is a very clear understanding that that was supposed to be a relatively short-term project. It's gone on for 2 years plus, and it has not worked out. Now, it's quite clear that it wasn't planned right in the first stage. And I think what is needed is a holistic approach, that you go from what you want to do, what problems are, what the engineering solutions are, and you go through it and you make sure that you don't get it wrong, so that it doesn't inconvenience people for longer than you would want it to.
Thank you, Professor Mitchell. We do have 2 more questions from the chat. To David Smith asks, does continuing to widen the junction road make good sense, or did we just underestimate the real cost of improving that road? Any takers on that one?
I would say that the problems of widening it were not understood, and the budget was not sufficient for it. That's what I would say with that situation. The geology there is the same sort of problems. You've got the shales dipping towards the road, so you're going to have that sort of problem. That hasn't happened yet, only in little bits, and that is a problem that's going to come in the future. I'll point out some of the other little things that you can see about it. They're putting up little walls on the side of the road. Okay, so when all of this material, which is the shales and sandstones, which you can see has already come off, that's going to come down, block the road, and there's going to be no way of pushing it off the road because you've got walls on the sides. So there's a whole stack of issues in there which aren't thought about. And I think that this is the planning needs to be better to begin with, so that you understand what you need to do and how you're going to go to basically a solution.
Thank you. Dr. Reed?
I think also that one has to take into consideration the traffic that is on the road. It's not all roads that need to be widened. It looks when you're doing road improvement, to what end? And there are a number of other routes across to the coast which are much more viable. And the Junction Road has for the last probably century been giving the Public Works Department in the first instance and National Works Agency a lot of problems. It's a known problematic route. And as Professor Smith has said, Professor Mitchell has said, the design that has been utilized there is apparently not suitable. You see a daily problem.
Okay, thank you. Thank you, Dr. Reed, and thank you, Professor Mitchell. We have another question from Shauna Lee Steele. Are regulations provided with hopes that individuals will find them and comply, or are there existing enforcement and monitoring procedures? And she added, especially in rural areas. Ms. McPherson, you want me to repeat that?
I heard what you just said. We are hopeful that with increased education, especially as it relates to the negative impact of landslide, we can get better compliance. But at NEPA, we also have an enforcement division, legal and enforcement division, that are currently active in the field, assessing and monitoring different aspects of development. We also have to remember that enforcement is largely carried out at the local level. So we depend heavily on the local authority to do a lot of the groundwork as it relates to enforcement. But NEPA is always willing, we're always in consultation with the local authority, trying to provide the support where necessary to increase the capacity and response as it relates to enforcement and monitoring.
Thank you, Ms. McPherson. Continuing with the last two questions we have from Jermaine Remiki. Given the obvious threats and dangers with hillside development, is there a recommendation that any hillside development must be done as according to the manual and not just that the manual is considered? I guess that's shared between Mr. Ricketts and Ms. McPherson. So they're asking, is there a directive or is it just there for consultation?
All right, thanks for that question, Jermaine. So the hillside development is a policy document. It's also a regulatory document. So in a sense, it really once there is a particular area that speaks to a particular challenge, it is a recommendation that is sent to the National Environmental and Planning Agency, the local planning authorities, and they act on that recommendation. So in a number of instances, we have a experience where several developments have been refused by the division due to non-compliance to the guidelines of the Hillside Development Manual. So it definitely has some amount of teeth. In addition, the Hillside Development Manual is also mentioned in the development orders. And so it, as I said, it does have some amount of teeth.
Thank you, Mr. Ricketts. And our final question for the evening, does tire soil have any fire risk?
Interesting. Interesting question, but very relevant, right? Yes, there is a risk to the tire soil retaining wall. If it is exposed, definitely there is, right? However, the finished grade is generally covered by free draining material. So from the top, you might not have such a high risk because it's covered. However, from the sides, it's exposed, and yes, there is a risk of fire.
Thank you, Mr. Ricketts. So that brings us to the almost end, but the close of the presentations and the question and answer for this evening's panel discussion. Forum, Science for Today Forum. And I'd like to offer my thanks to not only just the persons who are very obvious, namely our presenters, Professor Simon Mitchell, Mr. Knut Ricketts, Ms. Dan McPherson, and Dr. Wayne Reed. Professor Mitchell from the Department of Geography and Geology at the University of the West Indies Mona campus, Mr. Knut Ricketts from the Mines and Geology Division, Ms. McPherson from the National Environment and Planning Agency, and Dr. Wayne Reed from Gentech Consultants. But those are the persons you have seen. They're persons behind the scenes. And first, we'd like to offer our thanks to the support of the Dean of the Faculty, Professor Michael Taylor, who has been following on YouTube. I saw his comment thanking the presenters. We'd also like to acknowledge from the Dean's Office another force behind this evening's event, Mrs. Terry Ann Collins Frey from the Dean's Office Secretariat. She was keeping the correspondence going and making sure everything was in place. We'd like to thank Mr. Theodore Winter, our IT specialist, who made sure we all stayed connected and Zoom and YouTube worked together and we all stayed online and everything was seamless. We'd like to thank Dr. Andre Coy, the Associate Dean for Outreach, who is helping to monitor the YouTube channel and, of course, giving me nudges when I needed them. We'd like to thank the head for the Department of Geography and Geology, from where this nucleus of an idea for today's forum started. That would be Dr. Donovan Campbell. Thank you for your early encouragement to get this forum going and to find the speakers and to have it, because it's most topical and very interesting. And it is now upon me to thank the most important element of this evening, which would be the audience. We could have all the great presenters and all the great material and no one listening. At my check, we had 59 persons in at the highest. Maybe I missed when we hit the 60, but my last highest count was 59 on YouTube. And so we'd like to thank those persons who took the time to join us and share in this evening's forum. And just for me to say, stay tuned, look out for the next offering from the Faculty of Science and Technology in our Science for Today Forum. Have a very good evening, everyone, and thank you for being with us.
Thank you.
Thank you.